In this module, we'll talk about Keras. So this will be an introduction to Keras. Keras is a deep learning framework for Python. It provides a convenient way to define and train almost any kind of deep learning model. It was initially developed for researchers with the aim of enabling fast experimentation. But interestingly, it has now grown and become not just for fast experimentation, but also for final deployment, deployment in production too. The person who developed Keras, now I can't pronounce his name very clearly, Francis Cholet, said, I started Keras for my own use, pretty much. That's where he started. He's a really brilliant person. You can watch some additional interviews that I have in the links in the course syllabus. And he's currently, Francis is currently working as an AI researcher at Google, and he's also at the core of Keras development. This is what he had to say about Keras. I definitely didn't expect it to grow so big. I kind of expected it to make a bit of a splash in the small community of people using deep learning at the time in March 2015. A few thousand people. But back then, no one really expected deep learning would gather such an interest over the following few years. So he didn't expect Keras to become such a popular library at the time. Now the question is why Keras became so popular. Let's look at an example. Say, for example, I have a data set. Now I have rotated this by 90 degrees, but let's say these are my input columns, right? So first input column, second input column, third, da da da. And here's my output. And I want to design a neural network, right? So design a neural network that can predict a score based on these inputs. So I can calculate this, predict this quality accurately. With the native TensorFlow code, we have to write a lot of things. We have to write our own function to define how the loss is calculated, how the gradient is done, even creating new variables is not straightforward, and so on. What Keras did was squeezed all of this into a few simple lines of code. And that's what made Keras very popular, because now instead of doing all of this, I can very quickly say, create a neural network with, let's say, a few neurons in the first layer, a few neurons in the second layer, a few neurons in the subsequent layers, and still provide a lot of flexibility that developers want when designing their neural network models. Let's look at some features of Keras. It allows the same code to run seamlessly on CPU or GPU. So if you have a GPU, then you can run your code in GPU. But if you don't have a GPU, then even in CPU, your code will run without you changing anything. Now, things that usually run faster on GPU will run slower on the CPU, but it still runs. It allows you to very quickly prototype deep learning models. So you want to try a new model. Let's say I want to try a new deep learning model. Then I can very quickly do this using Keras. It has a built-in support for convolutional neural networks for computer vision. This will be the focus of our course as well. Recurrent neural networks for sequence processing, like natural language processing, and any combination of both. It also supports arbitrary network architectures, for example, multi-input, multi-output models. For example, one network model may accept text as input, image as input, right? And produce text, class, or many other things as output. Layer sharing, we'll talk more about that, and also model sharing. Overall, Keras is appropriate for building essentially almost any deep learning model, and it's currently one of the library to build deep learning models. The competitor, PyTorch, is also popular, but Keras I think is the most popular library. It also supports multi-GPU training. This is very interesting. Now that we are doing bigger and bigger trainings, having a support for a multi-GPU is very exciting. And Keras can be freely used in commercial projects because it has permissive MIT license. Let's look at where Keras sits in terms of the overall software architecture and maybe even hardware. Keras doesn't handle low-level operations, for example, tensor manipulation, differentiation, all those things Keras assumes that the underlying library does that. Two of the libraries that do this are Theano and TensorFlow. TensorFlow is developed by Google. Theano is developed by Mila Lab at University of Montreal. There's another one called PyTorch that's a similar library, a competitor. And then another one is CNTK. Now, Jupyter is a separate project developed by Jupyter. It's a non-profit organization. I think it was recently bought by another company. But overall, this is how things look like architecture-wise. At the bottom, you have your hardware, GPU or CPU. And then on top of the hardware, you either have Cuda, C-U-D-N-N, or BLAS. These are C++ level libraries that enable you to access your GPU or CPU resources. And then on top of that sits your Python programming language. And then on top of Python, you have your libraries like TensorFlow, Theano, CNTK, etc. that you can install. And then on top of TensorFlow sits Keras. And then on top of Keras, I would say not exactly on top, but on Python, you have your Jupyter notebook, where you can access Keras, TensorFlow, Python, all of them. And then that's where you are on top using the Jupyter notebook to write your program. Now let's talk a little bit about Cuda, because it's very interesting that Cuda allows you to run code faster in GPU. Cuda is a parallel computing platform and API model created by NVIDIA. So this is proprietary. You have to remember that because it doesn't work on other GPUs. Overall, C++ programmers use Cuda C and Cuda C++. If your code uses Cuda, then your code can be compiled not by using GCC, but by using NVCC, NVIDIA C compiler. It's NVIDIA C or C++ compiler. Overall, Cuda allows software developers and software engineers to use CUDA-enabled GPUs, graphical processing units, basically GPUs developed by NVIDIA, for general purpose processing. Anything that you want to do, you can do with Cuda, not necessarily machine learning or deep learning. And the cuBLAS library, this is Cuda BLAS library, is an implementation of the BLAS, which is a basic linear algebra subprograms. In other words, if you are using CPU, you would install BLAS to parallelize your mathematical operations. But if you're using GPU, then you can install cuBLAS in your GPU to parallelize your mathematical processing. It sits on top of the NVIDIA Cuda runtime, and it allows user to access the computational resources of NVIDIA GPU. Let's look at an example of how parallelization actually works using Cuda. Say we have a function called add that takes two integer arrays a and b, and it's supposed to element-wise sum them and insert the results into this third array. See, we have pointers here, so that there's no copying of data when calling the function, so that it's fast. Now there's a for loop runs from 0 to all the way to n, which is the number of elements, and then for each element I sum the element and put it to ci, right? So this is what we would do in a regular standard C++. If we have to do the same thing using Cuda, then the way Cuda works is, or like, this library, BLAS or cuBLAS work is that they will take this code or a code that somehow generates this code and break it down in the following way. Say this code needs to be broken down into two CPU cores, CPU core 1 and CPU core 2. Then we still have the same code, and we start with a variable called TID. Let's say we set it to 0, and while TID is less than n, we keep adding element-wise. So at the beginning, when TID is 0, we add element 0, A0, B0, and put it to C0. Then we skip 1 and increase TID by 2, so that next time we add A2, B2, and add to C2. In the next CPU, we actually start by TID equals 1, so that we add A1, B1, and put it to C1, and A3, B3 to C3, and so on. So you can see that we had these two arrays, A and B, and we were supposed to add element-wise from A, B to C, and what we did was all the even indices are handled by the first CPU core, and all the odd indices are handled by the second CPU core. In this way, whether you have a multi-CPU environment or a GPU with multi-core environment, Cuda and libraries that are related make use of multiple cores to parallelize any tensor operations that we want to perform.